Hi, this is Frank Coe, and I'm going to do a series parallel analysis with a new tool, screen capture, that's facilitated through Studio in Canvas. So I'm going to present a new circuit that I'm going to draw. Let's go ahead and do this guy this way, and put in a resistor here, put in a node, a resistor here, node, a resistor here, and another resistor here, and close this up. This will be my R1, this will be an R2, this will be an R3, this will be an R4. Now, given this, let's say we happen to have, let's develop this guy first. Let's make this guy 100 ohms. Let's make this guy 200 ohms. Let's make this guy 300 ohms. And let's go ahead and make this guy, that will be, let's go ahead and make this guy 50 ohms. And let's go ahead and make this source 20 volts. And our task is to do a complete VIR analysis. So very easy. We do a V column, an I column, and an R column. And we have 4 resistors, so we're going to have 5 rows, yes? Like so, like so, like so, and like so. So we have to have a row for R1, R2, R3, R4, and totals. Done. And then voltages will go here, currents will go here, and ohms will go in the last. So given what it is that we have, let's go ahead and fill in the values that we know in here so far. 20 volt source. We happen to have 50 ohms over here. We happen to have 300 ohms over here. We happen to have 100 ohms over here and 200 ohms over here. Now, in order to figure out the total and to do the rest of this, this is a series parallel circuit. Part of this is in series, part of this is in parallel. So the best way to resolve this is to look at a point, look at the circuit from a point farthest away from the voltage source. And that would be right here, looking at the circuit from this position back towards the voltage source. And when you look at this wire, what do you see? What are the components we see on this wire? Is this series? Are these components in series? Are these components in parallel? You want to simplify whatever you see first. And on this piece of wire, you have an R4, and it looks like R4 happens to have a single current path with R3. So perhaps it looks like these two guys may be in series. Yes, one current path from this node here all the way to this node. Well, by the way, why don't we go ahead and label these nodes? Let's go ahead and label this node A and label this, I don't like that pen. Let's go ahead and call this node B. So in this current path, it looks like we can simplify the circuit this way. So you're going to do this with redraw. You're going to have to redraw this a few times, so redraws. So this guy will simplify this way. When you do redraws, you want to draw the original circuit, or your redrawn circuit underneath the original circuit. So we're simplifying R3 with R4. So here is these guys simplified into a single equivalent resistance. And my original R1 stays here, my original R2 stays here, my original voltage source stays here, and it's 20 volts, that doesn't change. And these two guys are 3 in series. Oops, let me get the eraser. Okay, so R3 is in series with R4. These two guys combine to give you something called REQ number 1, right there. So we've simplified the circuit from 4 resistors down to 3. And again, we're looking at the circuit from this corner back in. And as we look at the circuit from this corner back in, check this out. You see an equivalent resistor REQ1, and it's attached to a node A at the top and attached to a node B at the bottom. What else? There's nothing else on that wire from node A all the way to node B, so it is a singular component. So what you're going to look at next is, well, what else is attached at A and B? Well, guess what? R2 is attached between A and B. That means that as you look at this, R2 and REQ1 happen to be in parallel with each other. So we're going to redraw this again. And as we redraw this again, we will have a point here, we will have a point here, and bring this guy down, bring this guy over to here, and draw this voltage source like so. And this is still 20 volts. This is still R1, that has not changed. It's still a 50 ohm resistor, like so. And since these have combined, this is R2 in parallel with REQ1. We call this REQ number 2. So let's go ahead and do some math here and see what comes of what we have. So if we said here in our redraw from the original that R2 is in series with R3, that means we're going to add 100 plus 200 gives you 300 ohms, which is what REQ1 is equal to. Now over here, since R2 was originally 300 ohms, this is 300 ohms, and it is in parallel with an equivalent resistance of also 300 ohms. R2 is in parallel with this, so what you have is 300 ohms in parallel with 300 ohms. You can use the shortcut of identical resistors, and you have two identical resistors. Divide that value by 2, so this REQ number 2 works out to be 150 ohms. You can use product over sum. You can also always use reciprocal method, but when you put 300 parallel with 300, you will calculate 150 ohms. So now in this last circuit, you only have two resistors that happen to be in series. One is 50 ohms and one is 150. Can you find the RT for the circuit after these steps? Sure you can. What is 50 ohms plus 150 ohms? Well, you know that to be 200 ohms. So I'm going to write down 200 ohms right there. And double check that. Remember, that's your first calculation as a result of series of circuit reduction via redrawing the circuit. And ultimately, as we look at this, 100 in series with 200 gives you an REQ1 that's 300 ohms. 300 ohms in parallel with 300 ohms gives us 150 ohms for this equivalent single resistance. So we have gone from 4 resistors in a circuit down to 3 resistors in a circuit, down to 2 resistors in a simple series circuit that allows us to calculate an R total. RT is equal to R1 plus REQ number 2. And if we wanted to write this out completely, our RT is equal to R1 plus, we happen to have R2 in parallel with these guys, R3 plus R4, close parentheses, close brace. That is your complete R total equation. So since we're happy with 200 ohms, we need to take, I'm going to put pause for a moment. All right, so we have 20 volts. That's going to be divided into 200 ohms, and that calculates to be 100 milliamps. And before you you can't fill in the entire column now because the entire circuit is not series. You can't fill 20 volts in the entire voltage column because the entire circuit is not parallel. Parts of this are in series, parts of this are in parallel. But let's double check this current since this is really, really important first calculation for us. Clear your calculator, take 20 and divide again by 200. And confirm your current. 100 milliamps, we are happy with that. We'll put a little dot right there just to make sure that we're happy with that. Now, what's helpful to you, watch this very carefully. Positive, negative, the electrons leave here, flow here, flow here, flow here, and flow back to the source. This is what happens in the basic simple series circuit. We have a sum of 50 plus 150 giving 200 ohms. 20 volts divided by 200 ohms gives you 100 milliamps. Now look at this very carefully. Does this 100 milliamps flow through any original resistor? Yes, it does. It flows through R1. We have 100 milliamps flowing through R1. This is the total current. So we bring that current here. We have 100 milliamps flowing to this node and coming back between there and there. The current that flows back through R1 is 100. Let's do this a little nicer. 100 milliamps. And we can bring this all the way up to the top. 100 milliamps leaves the source. And coming back through R1 is 100 milliamps coming back to the source. So we can tell from this basic redraw that 100 milliamps is flowing through the 50 ohm resistor. 100 milliamps. Guess what? You can now calculate V1 by multiplying 100 milliamps times your 50 ohms. And lo and behold, that works out to be a whopping 5 volts. Cool. We're getting there. Now, watch very carefully. We have 100 milliamps flowing out of the source at the bottom of the circuit, and then it runs into two branches. Part of the current's got to split to come up through there. The other part of the current's got to come up and split through here. Well, guess what? You can do current divider and find out how much current goes through each branch. But hey, since this is 300 ohms and this is also 300 ohms, guess what? Equal resistance means equal split. So the 100 milliamp current flowing into node B will be split evenly between these two branches. So you will have 50 milliamps, and I need another color here. Let's try this and see if this will work, because I'm getting red all over the place. So I have 50. That's really bad. I don't like that. Okay, let's stay with red. Bear with me. I have 50 milliamps coming up through R2, and I also have 50 milliamps coming up through REQ number 1. Well, look at this middle redrawn circuit. Does our current analysis help specify any currents through any original circuit resistors? Guess what? We now know that 50 milliamps is flowing through an original circuit resistor called R2. 50 milliamps flows through R2. Here's R2, and I can put in 50 milliamps right here, right now, and that allows me to multiply 50 times 300. So let's go ahead and do that. 50 milliamps, 50, and second, double E, change sign 3, so 50 milli times 300. And that gives me 15 volts. Cool. 15 volts. And when you think about that, that'll work out beautifully, because we said VR1 was already going to be 5 volts. And if we just calculated that between point A and B, we happen to have 15 volts right here, 15 volts across R2. Don't we have 15 volts right here? And Kirchhoff's voltage law says this voltage has to equal the sum of these two voltages. You can also double check this way. Isn't 100 milliamps times 150 ohms going to give us 15 volts? Let's double check that. Let's go ahead and say VREQ2 is equal to 100 milliamps times 150 ohms. Double check that. So this times 150, guess what? That's equal to 15 volts. So we can calculate the 15 volts between point A and point B right here by using Ohm's law of 100 milliamps multiplied by 150 ohms. 15 volts here plus the 5 volts here does add up to a voltage source. So that confirms we got a firm 15 volts between point A and point B. Guess what? If you have 15 volts between point A and point B, we have the current that flows through, that is the same voltage across REQ1. More importantly, we discovered the current going through our EQ1 is 50 milliamps. If this is 50 milliamps, isn't 50 milliamps flowing through these two resistors in series? Watch this. Oops, come back here. We happen to have right here flowing in this direction 50 milliamps. And we had flowing in this direction also 50 milliamps because we had 100 milliamps coming in. This tells you that through these two resistors, you have 50 milliamps flowing through each of those. R3 gets 50 milliamps flowing through it. R4 gets 50 milliamps. So 50 milliamps and 50 milliamps. Boom, boom. And let's go ahead and do this. Multiply 50 milliamps times 100 ohms. And that gives you 5 volts on this particular guy. And then 50 times 200 will give you 10 volts over here. And let's see if that makes sense. Let's bring this all the way up to the first circuit. Oh no, messed up. Momentary hiccup. Anyway, got the original screen back. So what I was saying was, let's go ahead and double check these voltages around the original circuit. We have a 20 volt source. Boom. We happen to have 5 volts up here. We happen to have 15 volts over here. 5 and 15 adds up to 20 in that loop. 15 volts is parallel to these two resistors in series. Well, in this resistor, we happen to have 5 volts, and in this resistor, we happen to have 10 volts. So 5 volts plus 10 volts between point A and B going on this loop on the far right-hand side adds up to 15, which is in parallel with 15. The VIR chart is complete. The circuit is solved. You are done.